Welcome to our exploration of magnetism and matter. Magnetism is a fundamental force of nature, influencing everything from the compass in your hand to the data stored in your computer. In this chapter, we'll unravel the mysteries behind magnetic fields, the behavior of materials in magnetic environments, and the real-world applications that make magnetism so essential. Whether you're curious about how Earth's magnetic field protects us or how magnets power modern technology, this journey will deepen your understanding of the invisible forces shaping our world. Let's begin by understanding the basic building blocks: magnetic field lines. Magnetic field lines are imaginary lines that represent the direction and strength of a magnetic field. They emerge from the north pole of a magnet and curve around to enter the south pole, forming closed loops. The density of these lines indicates the strength of the magnetic field. The closer they are, the stronger the field. These lines never intersect and provide a visual tool for understanding how magnetic forces act in space. By studying the patterns of field lines, scientists can predict how magnets will interact and how materials will respond to magnetic influences. Magnetic dipole is a system with two equal and opposite magnetic poles separated by a distance. The simplest example is a bar magnet, which has a north and a south pole. The strength of a magnetic dipole is measured by its magnetic moment, which depends on the pole strength and the distance between the poles. Magnetic dipoles are fundamental to understanding how magnets interact with each other and with external magnetic fields. They are also the building blocks for more complex magnetic phenomena in materials and devices. When a magnetic dipole is placed in a uniform magnetic field, it experiences a torque that tends to align the dipole with the field. The torque, tau, can be expressed as the cross product of the magnetic moment, mu, and the magnetic field, b. Tau equals mu times b. This torque is responsible for the alignment of compass needles with Earth's magnetic field and is crucial in the operation of many electromagnetic devices. Understanding this relationship helps explain the behavior of magnets in various environments. Bar magnet and a solenoid, a coil of wire carrying current, share similar magnetic field patterns. Both produce field lines that emerge from one end and loop around to the other, resembling the field of a dipole. This analogy helps us understand that a solenoid can act like a bar magnet, with a defined north and south pole. The strength and direction of the magnetic field in a solenoid depend on the current and the number of turns in the coil, making it a versatile tool in electromagnetism. Magnetic field due to a bar magnet can be mathematically described at any point in space. At a distance r from the center of the magnet, the field's strength depends on the magnetic moment and the orientation. The field is strongest at the poles and weaker farther away. This expression allows scientists to predict the influence of a bar magnet on nearby objects and is fundamental in designing magnetic devices. Field lines form characteristic loops from north to south, illustrating the dipole nature of the magnet. Earth itself acts like a giant bar magnet, with a magnetic field that extends from the core out into space. This field protects us from harmful solar radiation and guides navigation for animals and humans alike. The magnetic field is not perfectly aligned with the geographic poles, leading to phenomena like magnetic declination. Understanding Earth's magnetic field is crucial for navigation, communication, and studying the planet's interior. Magnetic declination is the angle between geographic north, true north, and magnetic north. This angle varies depending on your location on Earth and changes over time due to shifts in Earth's magnetic field. Navigators must account for declination to ensure accurate compass readings. Understanding declination is essential for map-making, navigation, and even for calibrating scientific instruments that rely on magnetic orientation. Magnetic inclination, also known as dip, is the angle that Earth's magnetic field makes with the horizontal at any location. At the magnetic equator, the inclination is 0, while at the poles, it is 90 degrees. This property is important for understanding how compasses behave in different parts of the world and for interpreting geological records of Earth's magnetic history. Inclination affects navigation and helps scientists study the movement of tectonic plates. Horizontal component of Earth's magnetic field is the part that lies parallel to the surface of the Earth. It is this component that compasses respond to, allowing for reliable navigation. The strength of the horizontal component varies with latitude, being strongest at the magnetic equator and weakest at the poles. Understanding this component is vital for navigation, geophysics, and for designing sensitive magnetic instruments. Magnetic susceptibility is a measure of how much a material will become magnetized in an applied magnetic field. Materials with high susceptibility are easily magnetized, while those with low or negative susceptibility resist magnetization. This property helps classify materials as diamagnetic, paramagnetic, or ferromagnetic. Understanding susceptibility is key in material science, especially when designing devices that rely on magnetic properties. Relative permeability is the ratio of the permeability of a material to the permeability of free space. It indicates how easily a material can support the formation of a magnetic field within itself. Materials with high relative permeability are excellent conductors of magnetic fields, making them useful in transformers, inductors, and electromagnets. This property is crucial for engineers and scientists working with magnetic circuits and devices. Magnetic materials are classified into three main types: diamagnetic, paramagnetic, and ferromagnetic. Diamagnetic materials are weakly repelled by magnetic fields, paramagnetic materials are weakly attracted, and ferromagnetic materials are strongly attracted and can retain magnetization. Each type has unique properties and applications, from MRI machines to permanent magnets. Understanding these differences is essential for choosing the right material for a specific magnetic application. Hysteresis curve shows how the magnetization of a material changes as an external magnetic field is applied and then removed. It reveals important properties like retentivity and coercivity, which determine how well a material can retain magnetization and how much field is needed to demagnetize it. The shape of the hysteresis curve is crucial for selecting materials for permanent magnets and magnetic storage devices. Retentivity is the ability of a material to retain magnetization after the external field is removed, while coercivity is the amount of reverse field required to demagnetize the material. Materials with high retentivity and coercivity are ideal for permanent magnets, while those with low values are used in temporary magnets and electromagnetic devices. These properties are vital for designing magnetic storage, transformers, and electric motors. Permanent magnets are materials that maintain a persistent magnetic field without the need for an external power source. They are made from materials with high retentivity and coercivity, such as certain alloys of iron, cobalt, and nickel. Permanent magnets are used in countless applications, from refrigerator doors to electric motors. Their ability to provide a stable magnetic field makes them indispensable in technology and industry. Electromagnet is a type of magnet in which the magnetic field is produced by an electric current. Unlike permanent magnets, electromagnets can be turned on or off by controlling the current. They are made by winding a coil of wire around a core, usually of iron, and passing current through the wire. Electromagnets are widely used in devices like electric bells, relays, and MRI machines, offering flexibility and control over the magnetic field. Permanent magnets and electromagnets serve different purposes. Permanent magnets provide a constant magnetic field and require no power, making them ideal for static applications. Electromagnets, on the other hand, offer adjustable strength and can be switched on or off, making them suitable for dynamic applications. The choice between the two depends on the needs of the device, such as whether flexibility or consistency is more important. Magnetic shielding involves using materials to block or redirect magnetic fields, protecting sensitive equipment from unwanted magnetic interference. Materials with low magnetic permeability, such as mu metal, are commonly used for shielding. This technique is essential in medical devices, scientific instruments, and even in protecting credit cards from magnetic damage. Effective shielding ensures accurate measurements and reliable operation of electronic devices. Magnetism plays a vital role in our everyday lives. From the simple refrigerator magnet to complex MRI machines in hospitals, magnetic principles are at work all around us. Electric motors, speakers, credit cards, and even trains use magnetism for operation and control. Understanding how magnetism is applied in daily life helps us appreciate the technology we often take for granted and inspires innovation in new fields. Study of magnetism is crucial in physics because it reveals the fundamental interactions between matter and energy. Magnetism is intertwined with electricity, forming the basis of electromagnetism, a cornerstone of modern physics. Insights from magnetism have led to breakthroughs in communication, transportation, medicine, and computing. By understanding magnetic phenomena, physicists can develop new technologies and deepen our knowledge of the universe. Magnetic domains are small regions within a material where the magnetic moments of atoms are aligned in the same direction. In unmagnetized materials, these domains are randomly oriented, canceling each other out. When exposed to a magnetic field, the domains align, resulting in a net magnetization. The behavior of domains explains why some materials can become strongly magnetized while others cannot. This concept is key to understanding ferromagnetism and the process of magnetization. The process of magnetization involves aligning the magnetic domains within a material. This can be achieved by placing the material in a strong external magnetic field, causing the domains to rotate and align with the field. Once the external field is removed, some materials retain this alignment, becoming permanent magnets. The ease with which a material can be magnetized depends on its composition and structure, influencing its use in various applications. Demagnetization is the process of removing or reducing the magnetization of a material. This can be done by heating the material, applying a strong reverse magnetic field, or physically striking it. Demagnetization is important in resetting magnetic devices, recycling materials, and ensuring the proper functioning of sensitive equipment. Understanding how to control magnetization and demagnetization is essential in many technological fields. Magnetic materials are at the heart of many technological advancements. Hard drives, transformers, electric motors, and sensors all rely on the unique properties of magnetic materials. The choice of material, whether soft or hard magnetic, affects the efficiency, durability, and performance of these devices. Engineers carefully select materials based on their magnetic properties to optimize device functionality. Soft magnetic materials are easily magnetized and demagnetized, making them ideal for use in transformers and inductors. Hard magnetic materials, on the other hand, retain their magnetization and are used to make permanent magnets. The distinction between soft and hard materials is based on their coercivity and retentivity, which determine their suitability for different applications in electronics and industry. Magnetic storage devices, such as hard disk drives and magnetic tapes, use the principles of magnetism to store and retrieve data. Information is encoded by magnetizing tiny regions on the storage medium, which can be read by sensitive magnetic sensors. The reliability and capacity of these devices depend on the quality of the magnetic materials used. Magnetic storage remains a cornerstone of modern computing and data management. Magnetism has revolutionized medicine, especially through technologies like magnetic resonance imaging, MRI. MRI uses strong magnetic fields and radio waves to create detailed images of the body's internal structures. This non-invasive technique has become essential for diagnosing diseases and guiding treatment. The development of medical magnets has improved patient care and expanded the possibilities of medical research. Magnetic principles are used in transportation systems like maglev trains, which float above tracks using powerful electromagnets. This reduces friction, allowing for faster and smoother travel. Magnetic brakes and sensors also enhance safety and efficiency in vehicles. The application of magnetism in transportation demonstrates its potential to transform how we move people and goods. Communication technologies, such as telephones and radios, rely on electromagnetism to transmit signals. Coils, magnets, and electromagnetic waves are used to convert sound into electrical signals and back again. The study of magnetism has enabled the development of wireless communication, connecting people across the globe and driving the information age. Industrial processes use magnetism for sorting, lifting, and separating materials. Magnetic separators remove impurities from ores, while powerful electromagnets lift heavy metal objects in scrapyards. These applications improve efficiency, safety, and productivity in manufacturing and recycling industries, showcasing the practical value of magnetic technology. Security systems often use magnetic sensors to detect unauthorized entry. Magnetic strips on credit cards and ID badges store information securely, while magnetic locks provide reliable access control. The use of magnetism in security ensures the safety of people, property, and sensitive information in various environments. Speakers, headphones, and microphones all use magnets to convert electrical signals into sound, and vice versa. The quality of audio devices depends on the strength and design of the magnets used. Magnetism also plays a role in video recording and playback, making it an integral part of the entertainment industry. Scientific research uses powerful magnets in particle accelerators, nuclear magnetic resonance, NMR, spectroscopy, and other advanced instruments. These tools allow scientists to probe the structure of matter, study fundamental forces, and develop new materials. The ability to generate and control strong magnetic fields is essential for pushing the boundaries of knowledge. Many animals, such as birds and sea turtles, use Earth's magnetic field for navigation during migration. Magnetoreception, the ability to sense magnetic fields, is a fascinating adaptation that helps these creatures find their way across vast distances. Studying magnetism in nature provides insights into evolution and the interconnectedness of life on Earth. Electric generators and transformers rely on the principles of electromagnetism to convert mechanical energy into electrical energy and vice versa. The movement of coils in magnetic fields produces electricity, powering homes, industries, and cities. Magnetism is at the heart of modern energy systems, making it vital for sustainable development. Magnetic fields can both store and erase data. Secure data destruction often involves exposing storage devices to strong magnetic fields, rendering the information unreadable. Understanding the interaction between magnetism and data is crucial for protecting sensitive information in the digital age. Artists and designers use magnets in creative ways, from kinetic sculptures to interactive installations. Magnetic paints and materials allow for dynamic displays and innovative forms of expression. The intersection of magnetism and art demonstrates the versatility and inspiration that science can bring to creativity. Educational tools and experiments often use magnets to teach fundamental concepts in physics. Demonstrations of magnetic fields, forces, and materials help students visualize and understand abstract ideas. Hands-on learning with magnets fosters curiosity and a deeper appreciation for the wonders of science. Ongoing research in magnetism leads to new materials, devices, and applications. Innovations like superconducting magnets, magnetic levitation, and spintronics are pushing the boundaries of what's possible. The study of magnetism continues to inspire breakthroughs in technology, energy, and medicine. As technology advances, the role of magnetism will only grow. From quantum computing to renewable energy, magnetic principles are at the core of emerging fields. Understanding magnetism equips us to tackle future challenges and harness new opportunities for progress and sustainability. Let's review the key concepts covered in this chapter: magnetic field lines, dipoles, torque, Earth's magnetic field, types of magnetic materials, and the differences between permanent magnets and electromagnets. We also explored the importance of magnetism in daily life and its applications in technology, medicine, and industry. Mastering these ideas provides a strong foundation for further study in physics and engineering. Magnetism is a fascinating and essential part of the physical world. From the smallest particles to the largest planets, magnetic forces shape our environment and drive technological progress. By understanding the principles of magnetism, we gain insight into the workings of nature and the tools to innovate for a better future. Keep exploring, and let the wonders of magnetism inspire your curiosity and creativity. If you're interested in learning more, consider exploring advanced topics like quantum magnetism, superconductivity, and magnetic resonance. These areas open up new frontiers in physics and engineering, offering exciting opportunities for discovery and invention. The journey into magnetism is just beginning. There's always more to learn and explore. Thank you for joining us on this journey through magnetism and matter. We hope you found the concepts engaging and the applications inspiring. Magnetism is all around us, shaping the world in ways both visible and invisible. Stay curious, keep learning, and remember, the power of magnetism is always within reach.